Very much, Arthur. Good afternoon, ladies and gentlemen. Thank you for staying on right to the end to hear the talk we've got about mine closure this afternoon. We have got a group of very interesting speakers lined up, and we'll take you through a range of topics. I'm just going to start with a bit of an introduction to mine closure to give you some insight into some of the concepts. It's becoming an increasingly more important feature of the mining industry, and as we've seen in the earlier talks this afternoon, that the overall performance of the mining industry needs to improve, the way it looks after itself and its environment, and the way it's perceived in the world. If we're going to sustain the mining that our economies need and attract people into the business, we need to be more serious about many aspects of the way that impacts on people's lives. So I'm going to take you through a few points here, and you can obviously read the slides at your leisure. I'm not going to read them. I'll just make a few points about each slide. I think the main thing to consider about mine closure is that it's all about restoring the land to a beneficial and sustainable use. So it's really about trying to reduce as much as possible the impact that the mining has had on that area, and to try and leave something behind that's positive. And it's obviously something that's developed a lot over the last sort of 50 years particularly, and the recent focus is to consider more socio-economic impacts, and that certainly has a real relevance in Kazakhstan because of the existence of so many towns that are solely dependent on one or two mines and processing operations, and obviously we call those mono towns, and that's something that increasingly is going to have to be addressed in Kazakhstan, as many of these operations will have to face closure soon, and historically that's not been so much the case. There has been a few mines closed successfully in Kazakhstan, but it's less so the larger towns, and I think in the next 10 or 20 years there's certainly be some of the larger mono towns will have to face the closure obstacle. There we go. Just to talk about a few elements about good practice for mine closure. One of the most important things to do about closure is to consider it as something that's integrated in the planning and operation of a mine. It's not something that just happens at the end as a discrete activity. The best operators will be almost thinking about, well, they will be thinking about closing the mine on the first day it opens and progressively closing it. And I think it's very important, it's very good practice to consult the stakeholders involved in the project about the closure needs for the local environment and the local industries that might replace the mining operation. And there's two sort of clear parts to it. There's the technical plan, all about what needs to be done, how it can be done, and how it can be done progressively. And then there has to be a financial plan, because obviously it's something that has to be paid for ultimately. And the current practice is obviously to set aside money in order to do that. And I think another key feature of good practice is updating the closure plan at a regular interval. And I think one of the benefits of doing that is if a mine is progressively closing facilities and rehabilitating, then the bill for closure at the end of the operation will be reduced. And I think that's a real incentive for mining companies to consider closure more seriously. Now, I'm not going to go through this slide. You've probably seen a few flow diagrams, triangles and geometric shapes today. But I think really the key point about this slide is that there has to be a balance between incentives for closure and penalties. And as regulators and as mine closure practitioners, we need to be aware of what those penalties can be or should be, and what incentives there are for a good closure plan. Now, if we just consider Kazakhstan for a moment, that certainly I think that it's something that I've observed that closure is something that just happens at the end, and I think that changing that will produce a lot of positive benefits. Sorry, I'm rushing through these slides here, but I don't want to detract from the time available on some of the other speakers that we have. I mean, looking forward, obviously, as I've mentioned, that closure needs to include the social aspects and be integrated with operations as they're carried out on a daily basis. So, for example, that could be something like mine waste dumps, that they're progressively covered with topsoil and rehabilitated during the operation. And it's not an activity that takes place at the end, because you can test, for example, what vegetation will grow best on that dump and actually get some experience of closure and closure operations during the mine operation when there's a full staff to carry out a lot of these activities. So it's a good opportunity during operations to do that. And obviously good practice, as I mentioned, is very important. Oh, sorry. And I think we have to consider as well that every mine is different. Every mine is going to have different opportunities for closure. And there are opportunities and benefits with every type of mine, every type of environment where you can consider different perhaps benefits from the closure of that operation. So I'm just going to leave it there. That's just enough of my brief introduction. And now I'd like to introduce the next speaker, who's a colleague of mine, Sandy. She's going to talk about mine closure requirements in more detail, and hopefully we'll get some time for questions at the end. So thank you.
Здравствуйте, уважаемые дамы и господа. Меня зовут
Good evening, ladies and gentlemen. Sandukash Abdijalilova, environmental consultant in SRK Consulting, and I'm representing international consulting company dealing with consulting services in the sphere of mining and metallurgy. We cover the entire life cycle of mines from the stage of geo-exploration and up to the closure. This panel session will discuss this very important topic, and we are going to talk about the closure of operation and closure of operation on subsoil use. The presentations that we are providing will be presented by me and Nikolai Kirillov, and the topic of this presentation is a transition to new standards of closure and recovery of land. In this presentation, I would like to share on the key requirements establishment in the legislation. And my colleague Nikolai will speak about practical steps to improve the practice of closure in Kazakhstan and in general in Central Asia. This presentation today covers the closure projects and exploration and mining of solid minerals. And I believe first it should be mentioned in the beginning as within subsoil and subsoil use code, we know that the legislation has been broken into three big blocks. It's hydrocarbon raw materials, solid waste, and uraniums. But today we are talking about solid minerals. We have to mention that the legislative framework in Kazakhstan is very well developed, and the issues of closure after exploration and mining of solid minerals are deeply integrated in every aspect and branches of our legislation. SRK Consulting operates all over the globe. The office in Kazakhstan also available. This office is active in Central Asia and CIS. We know the legal framework of this region very well, and we can say that in Kazakhstan the closure issues are very well included in the fundamentals of all the pieces of legislation. On the slide you can see the biggest laws and codes where we can see the requirements related to mine closures. Mostly these approaches are based on the provisions of subsoil and subsoil use in accordance with item 4, article 54 on the termination of a license or contracts for exploration and mining of solid minerals do not relieve the operator from the responsibility for the closure and liquidation of the consequences. The specifics is discussed in a special part of the code, and we have separate articles devoted to that. The provisions on the closures are also included into the environmental code, especially in its new version. We have separate article and separate chapters on the closure. And the key idea of this piece of legislation is a requirement that the closed object should ensure population safety, environment protection, and efficient land use. I'll not go through all the laws, but I'll mention that within the framework of the Water Code, conservation of existing facilities that may have negative impact on the water resources carried out in accordance with the approvals and in coordination with the basin inspections. The key focus of presentation will be the closure, and also we have to discuss the closure of exploration. Actually, this is done through reclamation of disturbed lands in accordance with the land code. The subsoil code provides that the person whose subsoil use right is terminated at this area of exploration must recultivate and close no later than 6 months after the termination of the license. At the same time, we have to note that this time frame can be increased depending on nature or climate and weather condition. If the subsoil user did not perform exploration but had a license for exploration and does not plan to perform the exploration, then reclamation requirements will be released. A reclamation should be accepted by the Commission to be established by local executive authority and registered with the Acceptance Act. For solid minerals projects, a plan of reclamation is a must requirement. So the consequences which are not included in the plan should be prohibited. We know that the plan should be progressively updated in the course of the life cycle of mine, but at least every 3 years, and at any update of mining plan. Here we have to mention that working in mining sector, we have observed a lot of closure plans, and we studied them, and we observed strong and weaker sides of closure plans existing in the industry. But I like to mention that in the beginning of operation of mine, closure plan is conceptual, but in the course of the progress, it becomes more and more complete, contains more and more details. It is important to include specialized surveys like climate surveys and geochemical surveys, and also we have to consider physical and chemical stability. We have to note that assessment of cost is a must condition of a closure plan, and the closure cost should be updated all the time.
Now speaking about the closure itself. It has to take place in compliance with the project designed on the basis of the latest relevant closure plan or liquidation project, but not later than 2 years before the end of the project. The code includes provisions that it has to start not later than 8 months before the expiration of the license on subsoil use. And again, The document has to be signed. The act on liquidation has to be signed. An important aspect include financial pledge. My colleague Nikolai is going to speak about it. Let me simply say that subsoil users is totally responsible for funding the liquidation, and this is the requirement of the code. There are three types of financial instruments: guarantee, banking deposit, and insurance policy. So the company is pretty flexible and can take any option. In terms of financial guarantee, the code specify a plan. We develop and expand our liquidation foundation with the progress towards the end of the project. Towards the end of the project. Liquidation, we know that it includes the assembling of facilities, other facilities, storage facilities, tail storage facilities, recultivation, and restoration of waterways. An important aspect of post-liquidation monitoring, and all these actions have to be assessed at the stage of development of liquidation plan and to calculate the relevance of all these works because they're pretty expensive. Let me pass the floor to my colleague Nikolai.
Nikolai is going to talk about the transition to the new closure requirements.
Коллеги, добрый практически.
Colleagues, good evening. Thank you very much for staying here with us. So let me continue. And I will start with just 1 second. I will start with this slide where you see the graph or approaches to the requirements on liquidation, how it developed in the world. I'm not sure if you see, you probably don't see it, but the last point is the Liquidation Act in Colombia as of 1969. Which serve as a basis of liquidation procedure, where it is required for all mining companies to restore and recultivate the lands and everything relating to production. Since those days, and the chart shows pretty busy dots of legislation requirements followed by international provisions, and the chart ends with ICMM toolbox, which is an excellent set of documents allowing you to plan liquidation and recultivation. And to the left side, there is the new code, which was passed in 2016-2018, and the instruction on development of plan and cost estimate for closure. One of the key requirements integrated into all these documents, I'm going to focus on three, which I believe are the key, which includes the issue of mine closure based on the whole life cycle of the mining plants, like Mike mentioned before. The closure seems to be something far away. However, it may cost quite a lot, and it's and even a feasibility study taking this into consideration is extremely important to be able to assess how it impacts the project's NPV in general. So if the results are negative and the impact is significant, there are technical solutions that will help you to proceed with recultivation works. So the issue of closure, including financial and technical aspects, have to be considered from the earlier stages of project design. Let me give you an example. If the company plans some expansion with the capital costs of $100 million, such decision is not made by the company without going deeper into feasibility studies and approaches to that. And if we take it as a solution, project and design work on closure, for example, 50,000 to 100,000 to 100 million US dollars, or development, construction of a new plant, or development of a quarry, which will be used in the deposit. So it requires an effort. The second part of the plan includes such aspects as social and economic implications. Any mining company, in addition to the fact that the company is a taxpayer, the company is a jobs enabler, and many companies such as SRK Consulting, they have hundreds of thousands of employees working for them, and it would lead to social tension and socio-economic challenges. Again, the social aspects have to be planned ahead when you plan the closure, when you develop a closure steps. The company has to plan and costs for training and retraining and employment of personnel. And for Kazakhstan, it is important to take into account the issue of modern towns, which is quite a sizable settlement of people working for one company. And if this company is closed, people would lose their income, and this may lead to the problems. So it is a problem for the company, for the city, for the republic, for the structure, and the company has to think about it. The next aspect, it incorporates certain assessment and costs relating to closure within the whole life cycle of the project. Sandy and Mike mentioned before that mining projects are not statical. Once you launch the first plan of mining works, they are subject to changes, and you have to continue to assess and reassess how technical solutions can be applied, what kind of financial aspects have to be addressed, what kind of social and economic programs are available. Let me reiterate that these works have to be addressed, these costs have to be addressed in feasibility study and in policies of the company, social, environmental, or combined policies, and reflect mission and values pursued by the company. The next one includes assessment and management of long-term residual closure risks. In Kazakhstani realities, there are one or two scenarios. Once the works are completed, the company performs its obligations before its creditors and discontinue to be any longer responsible. In reality, in a fast-changing legal environment, there could be some long-term residual closure risks. For example, acidation of mines, which may impact sustainability of specific projects or specific deposits. So they have to be addressed through technical solutions again at the earliest stage from the moment of approval of the concept, first concept. And often we know that a plan which was developed at the earliest stage is simply moving along with the project from one folder to another. However, a good practice includes approaches to verification of such plans to make sure that they are up to date. And you need to I want to emphasize another important aspect. Introduction of new requirements is accompanied by a complex transition relating to accumulation of experience and database on recultivation for the companies, for a regulator, and for designer or consultancy companies operating in the market and offering these services. This slide shows a small infograph on the companies which in the next decade will face the closure, and it includes Kazakhstan as well. I'd like to emphasize here that the context of the crucial role of planning includes several elements. Where first of all is cost estimate, which is a balancing factor for closure costs to make sure that at the end of the mining works, the budget is no longer that big and you don't have to run extra costs. You can find many other examples on how it was implemented, but if you try to find an article where you would see a provision that the mining company reestimate or overestimated the costs on liquidation, I couldn't find something like that, and the situation is quite opposite, in fact, in reality. This slide shows direct costs, and the next slide will show indirect costs. This slide is based on our experience in Kazakhstan, given the projects that we work with in terms of technical audits of companies, in terms of preparation of a competent authority report, resource estimates, and feasibility studies. The orange color stands for those that are excluded from direct costs or are underestimated due to missing technical details or underestimate of the total volume of works. Typical issues I'm going to share with you include the following. The closure plan has to include alternatives or options, but quite often the project specifies unimplementable technical solution, or the second one, which is doable. And there are many projects which have a statement that an option, for example, for recultivation with the water way. I don't think there is any mining project where this would bring economic benefit.
This option I would not consider as a true alternative. As the next issue is progressive reclamations. The instructions pushes subsoil user to apply it, but based on our experience, considering the practice of closure used in Kazakhstan, This is a double-ended question. First of all, the cell of tailing dump or will be recultivated in the course of the operations at the deposit, and at the end of closure operations, this task will be lacking. And if we take the mining plan or any document, any other document, if we check them, if we check financial model, these costs are not included in the major cases. There is a reference in closure plan, and nothing is said in the mining plan or in the financial plan. What could be the outcomes? Actually, total amount of liabilities the subsoil user have calculated will be significantly less than the real cost to be borne in the cost of the work. And the second option, that due to particular reasons, progressive reclamation is not considered as an option, as it is technically unfeasible, and as mining facilities are designed in such a way that they are impossible for reclamation. But for me, it is a design problem in mining plans and impossibility to carry out progressive reclamations. The next item we often face is the exclusion of infrastructure objects which are not related to mining from the volume of assessment of liabilities, like administration buildings, repair workshops, warehousing facilities, and the facilities for fuel storage that are taken aside of plan of closure as considered to be are not included into the closure plan. So these are possible options if we have third parties that can take that has been consulted and that can accept such facilities on its balance sheet, but most often we do not have any confirmation for such things, and the volume of liabilities is significantly decreased. And the next item, which is the most difficult from the point of view of accumulation experience and availability of practice, the unconfirmed technical solution. Usually design instruction is taken, and then the operators select options and applying the plan of closure. Some of them are not feasible, and some aspects are understudied, especially water balance of the objects after the stop operation. If the object will be flooded, then the issue is not considered to which extent the walls of open pit will be sustainable, and what will be the quality of water. And these technical solutions travels from year to different projects without proper explanation. And one of financial aspects, they use per item costs, and very often you'll find them in a table without explanatory documents. They have been taken from just the operator just specifies the price of demolition of 1 cubic meter of a building is a certain amount of dollars, and that raises doubts in the accuracy of such assessments. So unfortunately, the time present is for indirect costs. Indirect costs are often underestimated, and I can not say that it's done by purpose. Maybe it is a problem that depends upon the experience of a company and the experience of regulating authority and design companies deals with a plan of closure in accordance with international requirements. Here, just listen, this is just benefits payable to employees after the closure of a facility, and there were examples, and the firing of staff cost much more than the reclamation of land. And in practice, They include requalification of staff as a social and economic measures that would allow people to find jobs in other location or another profession. And another item is socio-economic programs related to more serious impacts like monotowns. And the last slide, I will be very brief about it. Where are the advantages of following the international approach and use global database? First of all, it's confidence in accuracy of the coastal closure. This is an advantage for subsoil users, regulators, and investors if this assessment made correctly, and we can see it in our work. Such assessments simplify audience financial models and accuracy of financial indicators of project. I'll not talk about progressive reclamation, and the next one is opportunity to use this data to assess current liabilities for closure, and I believe that your financial colleagues will be very thankful if the companies would do these assessments. And I would like to close with high note. Closure is not always bad, and we have a lot of good examples when new facilities were established at the place of an mine, when different alternatives were established, like Bitcoin farms, solar panel, wind panels, wind farms. And I would like to encourage you to use international experience, as global experience has been accumulated since 1969, and it's the time to do that. Thank you, colleagues.
I'd now like to introduce Eleonora, who is going to talk about smart sensing for ground movement.
Thank you very much. Good afternoon, ladies and gentlemen. As you are well aware, monitoring systems can provide data that can help reduce risk and obviously prevent accidents in many areas of mining operations, including tailing dams failures and slope failures. And we have seen in the last few years quite a few disasters, especially with the failures of tailing dams in South America and Brazil, where not only environmental disasters were occurring, but also the loss of human life. However, the traditional monitoring instrumentations and systems that we are currently using for in-ground monitoring of deformations, such as inclinometers, fiber optics, shape accelerated arrays, and for pore pressure measurements, the piezometers, rely on cables to send the signals and the data from the boreholes to the surface. Therefore, there are only few sensors that can be installed in the hole because of the size of the hole and the number of cables that has to be installed. The cables can and quite often get damaged when ground moves, and it is also quite difficult to install, for example, the piezometers and inclinometers at the same level or the same point when they are installed in the holes. Normally they are offset, and therefore they are measuring the ground deformation in a different point that we're measuring the pore pressure. So looking at this different difficulties with the wired systems, there has been a decision to look at the development of the wireless sensors that could actually measure ground deformation and pore pressure and send the data wirelessly to the surface. And the system, this type of system uses an ultra-low power in-ground radio mesh network markers, and each of the markers or each of the sensors is powered by the internal battery. The sensors measure basically the change in the tilt in 3 dimensions and the pore pressure as well as the temperature. And when the ground moves, the sensor sends data signal to the neighboring sensor, to the neighboring marker, and the signal is transferred upwards to the antenna on the surface and subsequently to the data logger. And here are some of the characteristics of the sensors. Well, internally, the basic components of the sensors is the accelerometers or the MEMS systems, the antenna, the batteries, and the pressure transducers. The physical dimensions is the weight of 1.3 kilograms and diameter of 65 millimeters. So basically, it looks it looks like this. It's not that heavy, but this is what it looks like in real life. It is quite robust. It can withstand blasting, and therefore it, even when installed, for example, in open pit mines behind the slopes after the excavation, after the blasting, it can be recovered and used again. Here is if I can move it, okay. Could we run the slide, please? Here's an example of how this system really works. It is an example for subsidence evaluation. However, it can, this example, the principles actually applies in any other applications such as the tailings or waste dam monitoring or slope monitoring. Could you please run that slide, that slideshow? No. You need to click on the, can you go back please? And click within the slide, within that picture. That one. Yes, thank you. So you can see that as the caving occurred and the toppling starts to occur, the sensor at the bottom is moving and is sending the signal to the sensor above it, and that signal is then transferred through the rest of the sensors to the ground, to the surface, to the antenna, and then to the data logger. The data obviously can be plotted, can be presented in such a way that it could be very easily understood. And in this particular examples, it's been showing that the deformation was occurring from the bottom through the middle to the top of the slope. Okay. Because it can send the signal wirelessly, the problems of possible in-hole cable breakage is really eliminated, or at least it's eliminated, it's reduced. But also because this device can withstand blasting, so it is quite robust. Then therefore its casing is not going to be deformed just because the rock moves. The sensor moves with the ground and detects the movement not only in horizontal tilt or vertical direction. And the signal, the data sent through to the surface then depends on which direction and which direction and whether it rotates and this sensor is moving. In addition, as the entire array of sensors is actually is installed, so it's not only 4 or 5 sensors like in the case of inclinometers or pore pressure, but these sensors are installed every 2 meters, even though they can transfer the signals up to, at the moment, up to 5 meters, but the installations usually provide for some redundancy in case any of the sensors moves out of range or something happens with its internal infrastructure. Then, therefore, this sensor arrays can actually monitor the deformation and the pore pressure in many locations, and the data acquired can provide basis for the risk assessment and for the prediction of the failure before even any movement of any deformation is detected on the surface, whether it's the surface of the slope of the open pit mine, or it is the embankment, the surface of the embankment of the tailing dams, of the waste dams. Some of the other advantages of this system of wireless smart markers is the fact that if the physical structure is growing or is expanding or is being expanded, for example, in the case of waste or tailing dams, additional sensors can be added, and these additional sensors then can be connected to the sensors that are already installed within those structures, and therefore there is no need to install a new array, a completely new array of sensors to monitor this expanded site. The data also can be accessed remotely, which can obviously reduce the number of personnel that needs to be on site and needs to monitor the system. And also the data, the process data, the information that we are actually gathering from these sensors then can be linked, can be sent to mine planning or monitoring software, and can be integrated with other monitoring systems on mine sites. So with the advantages of wireless signal processing or wireless data transition, the multitude of sensors that can monitor both the deformation as well as pore pressure and the temperature at the moment at the same point, this system really can complement what is currently being used in various applications and monitoring system on site. It can also complement the monitoring systems that monitor the behavior of the surface, or whether the waste dumps or the slopes, such as the radar or laser-based systems or satellite-based systems. So this data really could be quite crucial for the safety and the prevention of the accidents and the prevention of the disasters that we have seen in the last 7 years around the world. Thank you very much for your attention.
Thank you. Now I'd like to introduce Eugene, who's going to talk about the importance of monitoring legacy tailings. So, thank you.
Добрый день, уважаемые коллеги.
Good afternoon, distinguished colleagues. Let me offer you a presentation of Inside Terra company on the importance of monitoring legacy tailings. First of all, let me say a couple of words about who we are. Inside Terra is a software company which offers turnkey solutions and services on monitoring geohazard risks to ensure safety in tailings and in other facilities in mining sector. The service is based on a universal comprehensive platform which was designed by the company. The company is in close cooperation with different engineer records in a number of major mines. For example, in South Africa, the company Inside Terra works closely with the company SRK Consulting, which is the leader of this session. An important aspect of Inside Terra company includes assistance to the companies in compliance with global sectoral standards in tailings management, including closure of tailings. In this presentation, I would like to draw your attention to three key aspects or messages. Number one, the global standards on tailings management is applicable to all stages of life cycle, including closure and including post-closure periods of mine. The second focus, or the second message, includes an ongoing monitoring of legacy tailings facilities, which is equally important as monitoring of active facilities. And the third statement is about effective design, implementation, and operation of a comprehensive monitoring solution to reduce risks and balance sheet exposure, and enables a lower insurance premium and help achieve ESG compliance, as we discussed earlier today. Now let me move to digitalization in tailings management envisages remote monitoring, including data collection, transition of data, and most mining companies are quite active in introduction of this system into tailings storage facilities monitoring. I'd like to draw your attention to the slides. On the right side, you see regulation requirements of the national legislation and codes. In Kazakhstan, a couple years ago, they approved the rules for industrial safety for tailings, and they serve as one of the driving forces for introduction of monitoring. On the left hand, it is necessary to comply with the global sectoral standard, which is the second driving force for the system. And also shareholders and investors' pressures in terms of ESG. The previous session focused and dwelled on a lot about it. And the last driver includes financial structures in terms of financial risk management. Similar incentives and drivers can be applied to the tailings that are outside of exploitation. If we take examples of automation of tailings storage facilities in Kazakhstan, we can take Varvarinskaya tailings facility, where monitoring is widely used, including different types of meters for control and monitoring. At the same time, examples of comprehensive and integrative approaches to monitor TSF, especially if we take closed type of TSF. There are not so many in Kazakhstan, although the practical experience of TSF to address quite important issues such as safety, for example, and they are very important for sustainable development of mining industry in Kazakhstan. And again, we discussed it earlier. And actually, my presentation is a follow-up of the previous session. Now, let me emphasize the key message of my presentation, which says about global experience of in-ground monitoring sensors, which requires comprehensive approach with a combination of two technologies. And it is envisages the use of real-time and continuous data collected by sensors. And the second is optical sensors or drones and satellites, including infrared false color analysis in SAR. Tomorrow, my colleagues are going to present on that. Insight Terra created its own comprehensive system for monitoring for TSF and other facilities, which envisages application of its own equipment and outside equipment. And it allows to use physical inspection data from satellites 3. Speaking of the most popular types of monitoring, we will include water saturation and structural integrity of TSFs, water and air quality, and ESG criteria and parameters. Two last types of monitoring are linked with environment and with ESG criterion, which is a follow-up of requirements on monitoring. I also want to emphasize the synergy of cooperation of Insight and Terra company and Insight Power and SRK Consulting. As part of this cooperation to integrate partner solutions, the works on closure of mines can be extended, and extended works may include the planning of closure, which again was mentioned earlier. And also it can include integration of data, including archive data and geoinformation systems data, which could be integrated into this solution. Now I'm moving to the major slides, which demonstrate the Inside Terra monitoring solution and infrastructure system. It is a comprehensive cloud-based system which collects data from different sources, including outside sources, and they are intended for processing, visualization, and analysis of data based on legacy, based on historical data. Inside Terra solution is agnostic. It does not depend on the selection of a sensor. It defines the parameters for monitoring of interest and also which of the metering devices are most suitable. With our platform, we can integrate different types of monitoring systems, and the number of sensors, the list of sensors is extended on a regular basis. We bring it to common vision, in fact, the data collected from different sources. A lot of data is collected from the sensors, and it reduces the need to have extra communication and excessive communications. This slide shows TSF and sensors. Usually you have to have a set of sensors. First of all, let me highlight different type of edge data aggregation and communication system. Resilient satellite connectivity, custom dashboards, AWS. It allows you to monitor different hazards for potential slope transition, and also ultrasound and seismic sensors potentially can be integrated, equipped with accelerometers. They're intended to collect data with preset intervals, which is very important. And the ultimate goal is an alert on the upcoming hazards or potential hazards close to the set up parameters. Sensors enable transition of information through Wi-Fi to the server where this data is aggregated. The same server receives data from the other sources, the data from ERP client, archive, and many other. Then from aggregation server, the data goes through satellites or on-land channels. There are such channels, although it's a rare case, to the cloud-based Inside Terra storage. Inmarsat and Inside Terra has preferential tariffs for satellite transition of data. To the same platform monitoring solution Inside Terra, we collect sensor data from on-land monitoring systems.
After the data transmitted, they are processed, correlated, and in adjusted and structured form reach the screen or control panel. And I would repeat that the data may add each other, recheck each other, and in a proper algorithm type, they reach the platform for their further visualization. Inside Terra has an advanced application of visualization, and they demonstrate the status of visualization in real time. It allows to assess the reality of this risk, but the most important thing is not the visualization. The most important thing is timely informing the clients on the hazard. After approval of the client, inside Terra informs the border values of parameters, and if the indicators exceed these borders, or in the case of the trend of approaching the trend, the border, this information is delivered to, or alerts are given to a client. Timely information allows timely measures to remove the problem. And I would like to mention that inside Terra provide operational information and comprehensive operational reports in real time that allow us to see hazardous trends and prevent undesirable events. The platform inside Terra includes advanced risk forecasting algorithms, and this is the most important feature of solution of inside Terra. In conclusion, I would repeat the key sentences of my presentation. First of all, a requirement of GISTM should be applied for closed tailing dams. One of the requirements is ongoing monitoring of lasing dam facilities and effective design of legacy tailings provide significant economic effects. Thank you very much for your attention. I'll be happy to respond to your questions.
Eugene, I'd just like to introduce Francois Dutoy, who's going to provide our final talk of the session today, and he's going to talk about monitoring tailings facilities.
Good evening, ladies and gentlemen. My name is Francois Dutoy, and I'm a geotechnical engineering consultant in the tailings department at SRK Consulting, Kazakhstan, and I'm an associate member of the Australian Institute of Mining and Metallurgy. I have an academic background in both geology and geotechnical engineering, and international working experience in both the mining and construction industries. Today, I will be presenting a brief talk on TSF monitoring as an aid to TARP development for closure. Tailing storage facilities, or TSFs, can be considered large, permanent structures consisting of one or more dams for the storage of extractive mine waste, specifically tailings, and they are designed for stability decades after mining has been completed. During the operations phase, a TSF should be monitored to assess whether the expected performance of the design is achieved. As an example, the parameters that are commonly monitored to assess the stability of a TSF are displacement, pore water pressure, and the phreatic surface level. If the performance that is expected of the design is not met, a response plan should be implemented to avoid potential harm to downstream communities and the surrounding environment. The goal of the closure phase in the TSF life cycle is to leave the facility in a minimum maintenance condition, decommissioned and reclaimed, integrated into the surrounding landscape, restored to the natural appearance of the surrounding area, and with the pre-mine land use and level of productivity. But the reality is that the closed TSF should still be stable for decades or even centuries to come. The TSF landform will still exist, and even if the facility may be covered with an engineered and vegetated layer, it is essentially still tailings that are stored in a tailings dam. The key point is that the closure phase of a TSF requires design input, and the design has expected ranges of performance. Therefore, we can say that if the performance that is expected of the closure design is not met, a response plan should be implemented to avoid potential harm to downstream communities and the surrounding environment. The Global Industry Standard for Tailings Management, or GISTM, Principle 7, clearly states that closure should be considered part of the TSF lifecycle. GISTM Requirement 7.4 states that a response plan is required if the performance expected of the design is not met. Therefore, Principle 7, in conjunction with Requirement 7.4, can be interpreted as a TSF needs to be monitored in the closure phase and trigger action response plans, or TARPs, need to be available to address unexpected performance. A TARP is defined as the minimum set of actions required by workers in response to a deviation from normal working conditions. And the function of a TARP in the context of closure is to balance maintenance and remedial expenditures while safely managing the risks associated with the TSF. A TSF poses risks to the downstream community in terms of fatalities if a dam breach were to occur and a town was to be inundated, or livelihood if farmlands are inundated, or even illness if sources of drinking water are contaminated. Further, the environment is also at risk in terms of river pollution, soil pollution, or the contamination of fauna and flora. Infrastructure is also at risk where damage can occur to roads or bridges, or trade routes can be compromised and utilities can sustain damage. TARPs reduce these risks associated with TSFs by identifying trends of unexpected performance in monitoring data to preemptively warn of potentially hazardous situations developing, also by ranking the severity of the unexpected performance to avoid over or underspending on maintenance, remediation, or responses. They further also reduce the risk by defining response procedures to inform all concerned parties about the actions to be taken in case of a deviation from expected conditions, and also by identifying isolation areas in case of potential dam failures for the safe and timely evacuation of populations that are at risk, and by maintaining regular contact with downstream communities and emergency services to ensure that first responders have the most relevant and up-to-date information. But in order to identify unexpected performance, we first require knowledge of the expected performance, and this is acquired by analyzing monitoring data that is collected during the operations phase of a TSF. TARPs assess actual performance against expected performance and provide a response plan when the two do not align. The response plan is dependent on the severity of the unexpected performance, or the trigger level. The number of trigger levels assigned to a TARP depends greatly on the performance aspect that is being assessed. For example, erosion may only have 2 or 3 trigger levels, while slope stability TARPs may have 5 or more. Each level of a TARP should have clearly defined trigger levels and adequate responses to avoid ambiguity. And the higher the trigger level, the greater the exceeded expectation performance threshold. It should be noted that TARPs are unique to each mine and require specialist input to develop. The trigger levels of a TARP are informed by the potential unexpected performance, which is considered by tailings experts, and by historic monitoring data from TSFs collected during the operations phase, as well as external data. The corresponding response levels must be proportional to the trigger level to avoid over or underspending on maintenance and responses. They must also consider available resources to avoid response plans that cannot be executed, but they must also consider the time available for response to avoid response plans that cannot be executed in a timely manner. For the most severe levels of a TARP, a dam breach analysis is conducted to inform response plans. The end product of a dam breach analysis is inundation maps. These are used to define areas of isolation and to prepare emergency response plans with downstream communities and rescue services. Regular reviews and updates are required to optimize TARPs as performance data becomes available. Here is an example of a TARP summary for slope stability, based only on displacement measurements informing the trigger levels. The first trigger level is described as anticipated acceptable deformation. The trigger is detected movement within an acceptable threshold, and the response is to continue with routine monitoring. By escalating the level of movement, we might reach trigger level 4, which is described as potential failure development. The trigger is a failure date predicted within a specified time frame by the inverse velocity method, and the response is to distribute inundation maps and start evacuating isolation areas. The fifth and most severe trigger level is described as an unexpected failure. The trigger is a sudden, unpredicted slope failure, and the response is an emergency situation. A variety of data sources can be considered in the development of trigger levels for TARPs. The data can be split into 2 broad categories, namely internal and external data. Internal data is collected by monitoring the TSF performance during the operations phase. Common examples are displacement, pore water pressure, and phreatic surface level data. External data can be collected independently of the TSF, and some common examples are rainfall, wind speed, or seismicity measurements. Once sufficient data has been collected covering the operations phase of the TSF, it is analyzed for correlations. For example, developing a slope stability top could require displacement, pore water pressure, rainfall and seismicity data, and an erosion top may require rainfall and wind speed data and a record of observations made during routine inspections of the TSF in its operations phase, while a seepage top could require pore water pressure and phreatic surface data along with a record of observations made during routine inspections. The ideal format for measured data is standardized electronic format, and this can be readily achieved with automated monitoring systems as presented earlier during this session. The advantage of having the data in this format is reduced data cleaning and processing time, leading to faster pattern recognition and trend identification, and thereby a reduction of the time taken to develop TARPs. I would like to conclude with 3 final remarks. Firstly, TSFs are large permanent structures which retain the function decades after mining is completed, along with the risk of actual performance not aligning with the expected design performance. Secondly, TARPs reduce the risk associated through response planning. They are required by GISTM in the closure phase, and they are unique to each mine. And lastly, the development of effective TARPs relies heavily on specialist input, quality monitoring data from the operations phase, and close cooperation with all stakeholders involved in the closure process. Thank you very much.